Welcome to Caltech for those of you who are coming from out of town. My name is Harriet Bredel and I am the Exec Director at the Keck Institute for Space Studies here on campus. So before I kick off, I just want to see a quick show of hands. Who here has been part of a KISS short course study program activity in the past? All right, fantastic. And for who of you is this the first time being involved in a KISS activity? All right, okay, so we've got a good mix here, which is excellent. So with that, I'll give a quick introduction. So the Keck Institute for Space Studies, we are a think and do tank that is based here at Caltech. We work to bring together scientists and engineers and experts across different fields to develop innovative new space missions and technologies. And I think it's safe to say that the Interplanetary Laser Trilateration Network, as well as being slightly difficult to say, but I'm going to master it by the end of the week, is certainly one of those innovative mission concepts. So we're really excited to have you all here today. As well as short courses and workshop study programs that we support throughout the year, our core mission here at the Keck Institute for Space Studies is to help develop and catalyze those revolutionary ideas to shape the future of space exploration. So we look to do that through the study programs that we support throughout the year. Many of you here are going to be staying on for the rest of the week for our ILTN study program for the full week. We also look to build community, and I hope that we are going to have a growing community focused on this particular topic over the next few days as well. And we're also really keen to inspire the next generation of leaders in the space community, and so it's wonderful to see some early career folks here to join us as well. So before we kick off, this morning we have got a fantastic lineup of presentations that we're going to hear from today, all related to this topic around Interplanetary Laser Trilateration Network. We're going to kick off with one of our study leads, Bruce Bills, but before we do that, I just want to talk you through a little bit of the logistics to familiarize yourself with the morning. So just as a reminder, the exits are behind you. If you hear a fire alarm, please do follow all instructions. We are going to have 3 of our talks this morning before the break. We are then going to have a half-an-hour break from 10:45 to 11:15. We'll come back for our next 2 talks, and then we'll have lunch served outside as well. So with that, I'm really excited to introduce one of our study leads for this study program. Everything that you'll see throughout this week is thanks to the hard work of our 3 study leads, Chris, Marshall, and Bruce, so a huge thanks to them. Chris is going to be our MC for this short course and is going to be presenting each of the short course speakers. So with that, I would like to welcome Chris up to introduce our first speaker. Thank you, Chris.
All right. Thank you, Harriet. And thanks for the team for all that grueling help you gave us. It was remarkable to get to this point. I'm still amazed we actually made it. So thank you very much. Good morning, everyone. Without slowing down any further, it's a particular pleasure to introduce Bruce. Just cut and dry. A simple set of information about Bruce. He's a senior research scientist at the Planetary section of Science Division at JPL. He has been there for a long time. He's originally a Caltech product. He was a graduate student here, came to JPL afterwards, and then left for a while, and in the interim worked at Planetary Institute in Houston, at Goddard, and at Scripps Institute for Oceanography. He's a planetary geodesy expert with particular interest in orbital rotational dynamics. That's about it for cut and dry. Personally, I would say as a dear friend. Myself, I'm an odd person here. I'm actually mostly with history and cosmology, but through Bruce, I got involved in some of these dynamics and topics for the last few years at JPL. One of the pleasures of JPL to be able to meet people out of your normal walk of life. And this concept was on Bruce's mind for a very long time. He's going to give you an apt introduction to how we were thinking about it and what is it that we hope you to help us with to make it even better. So, Bruce?
Good morning. So I'm going to give a relatively brief introduction to interplanetary laser trilateration networks. And this ILTN abbreviation will crop up occasionally, but that's what I'm going to be talking about today and sort of is the main topic for this whole week-long workshop. And I'm going to try to briefly go through enough of a discussion of what is ILTN and how, in a very simple way, does it work. I don't actually pretend to know anywhere near as well as some of the other people in this room how well it could potentially work. But we're going to try and probe at, how well does it need to work in order to achieve the science that we'd like to see come out of it. Okay. How do I?
Yes. If you want to use this clicker right here.
Okay, thank you. Okay, so the basic notion is that we're going to send 3 spacecraft into orbit around candidate planets, and the nominal set are Venus, Earth, and Mars, although there are other considerations that might suggest other, targets, but that's the set that I'm going to be discussing. So getting them into orbit is sort of the first step. Then each of the 3 spacecraft has lasers on it, and it communicates with the other 2 spacecraft. So there are laser pulses going in both directions between each pair of spacecraft. And measuring the travel time of those laser pulses is sort of the main business of making the measurements. And again, how well we need to do that and how well we think we can do that are topics that are going to be discussed at considerable length later today and throughout the week. So here is a sort of a simple cartoon that shows the orbits of Mars at the bottom, Venus the upper right, and Earth on the left. And the red arrows are indicating laser pulses going in both directions along all 3 legs of that triangle. So this is kind of a pictorial representation of how this thing is supposed to work. Because the orbits are nearly circular, but the distances between the pairs of planets are changing appreciably over their orbits, the enclosed area in this triangle varies quite considerably over the course of the orbital motions. And the Sagnac effect, which is the difference between the travel times for laser pulses moving in prograde and retrograde directions. And that's sort of, at some level, the main thing that we're going to be measuring is, how not just the lengths of the links, but how is the enclosed area of this triangle varying with time. And another topic that the first figure I showed sort of doesn't represent at all. It just sort of shows the host planets as just little dots. But we need to understand in considerable detail how big an orbit do we need around Mars, and how big around Venus, and how big around the Earth, because there are consequences in terms of how accurately we will be able to know where the spacecraft is relative to the host planet, and it will quite significantly influence the cadence at which we can make these measurements. So this figure, which is kind of busy, but it shows a 70-year time span. And over that time span, it shows the enclosed area in square astronomical units on the vertical axis of this Venus-Earth-Mars triangle. And you can hopefully see that it varies a lot. There are times when it's very nearly zero. The three orbits are aligned in such a way that the enclosed area nearly vanishes. There are other times when the area, that the three planets are kind of as far apart as they get, and the enclosed area is large. And then there's sort of a, if you look near the top, the times at which the maximum area occurs are quasi-periodically spaced. So this is a slightly different representation of a related thing, which is the Sagnac time delay associated with these variations in the orbit geometry. And the little red dots at the tops of the oscillations highlight the fact that the maximum Sagnac delay, again, is very nearly periodic, with a period of a little over 6 years. And so there's a lot going on in there, and exactly how this cadence of time delay variations maps into the science signal that comes out is going to be a topic that we're going to hopefully get a good understanding of by the end of the week. So I already made the point that the enclosed area has significant variations, and these prograde and retrograde directions make it into essentially a giant ring laser gyroscope. In typical, those of you who flew into town for the meeting, you were on a big airplane that had a small ring laser gyro for navigation purposes, and they typically have an enclosed area of a few square meters. Ours has an enclosed area of 10 to the 15 square meters. So it's an enormous ring laser gyro, and it therefore has incredible sensitivity to measuring rotation rate variations. So for example, the local rotation rate associated with the galactic motion should be easily detectable with this instrument. And again, these effects have a dominant period of 6.4 years. So by making these measurements, we expect to, at first order, just know where the orbits of these three planets are, and we'll know how the geometry of those orbits changes. And we expect to be able to do very much better than is currently done in measuring those distances. The Deep Space Network sends microwave signals from the surface of the Earth to spacecraft either on orbit, around planets, or on the surface, and it does a pretty good job of measuring those distances. Our anticipation is that this proposed new system will do orders of magnitude better measurements just of those distances. And our improvement in solar system angular rotation rate is going to be many orders of magnitude. And so that's kind of what I was going to say. And I now have time for questions.